enthalpy. Enthalpy. Thank you, sir. Enthalpy. Okay. And actually, first thing to know about this is it's a state function. So again, whenever we say state function, you got to get into your head what that means. It means it doesn't matter what pathway went before. It doesn't matter what pathway went before. Andy.
Sorry.
It's okay. We're just checking to see. And what it's actually equal to is H equals E plus PV. So H is enthalpy. What's E?
Internal energy.
Internal energy. And PV is pressure, volume, work. Okay? Now here's the problem though. Can we calculate E?
No.
No. So this concept of what is enthalpy is kind of confusing because we can't really calculate that E. Okay. So enthalpy can be confusing, but we can make it a lot less confusing when we start talking about changes in enthalpy. Or delta H. And we'll be dealing with delta H for a while now. Something to get used to. So this is also a state function of a system. And here's where we're going to make it simpler. At a constant external pressure, delta H is equal to the flow of heat. When only PV work is allowed. So get that down and we'll kind of tear that apart and see what that's all about. Okay, so first of all, we're putting some constraints on this now, all right? We're saying enthalpy, not something we can really calculate, and it's kind of a tough concept because it has to do with internal energy, and you add to it pressure volume work. But changes in enthalpy, again, are a state function, meaning that the here and now is what's important. Okay, it doesn't matter what went before or went after. And if you keep constant the external pressure, then delta H is just equal to Q, or heat, when only pressure volume work is allowed. So I want you to think about that. That sounds like, oh boy, we're setting a lot of constraints here. But when you think about this, when you do an experiment over here in a laboratory, in general, you're doing it in the atmosphere. Follow me? All the experiments you've done in the atmosphere, right? That's a constant pressure. So we're talking about the conditions like when you say you light a firecracker off. And you want to figure out the change in enthalpy. Well, it's just going to be the flow of heat because the external pressure on the firecracker was just constant. Are you guys with me? Nobody? Okay. All right, so again, what I'm saying is we're setting up a set of conditions as like if you're doing an experiment on a lab bench. The pressure out here is constant for all practical purposes. Since the pressure out here is constant, enthalpy is no more than the flow of heat. You with me? We're making it simple now. So under these set of conditions. So we can say delta H is equal to Q P. Q sub P. This is change in enthalpy. Change in enthalpy. This is heat at constant pressure. And both of these are measured in joules or kilojoules. Now, this is kind of just get ahead a little bit for chemical reactions. So for chemical reactions, delta H would be equal to H of products minus H of reactants, which we will we'll get to that in more detail here in a little bit. Okay, so for later on, what we'll get into later is if I can figure out enthalpy values for what I start with and what I end with, the difference is the change in enthalpy or heat. Every time I say enthalpy right now, what should you be thinking? Flow of heat. Just don't get bogged down the word. Like when I say mole, you don't go, you go dozen, right? When I say enthalpy, you think heat. Okay. So again, if things come out positive, what kind of process are we talking about? Endo. And obviously, negative is XO. Okay. All right, so now the first kind of examples or problems you're going to be doing are kind of like this. Let's say I give you an equation, like phosphorus, which is a solid, P4 solid, reacts with 6Cl2 gas to form 4 PCl3 gas. And I give you a delta H value for this equation, and it's negative 1225.6 kilojoules. Can you see this is an exothermic reaction? If you react these two things together, you get a negative delta H. Now, the amount of heat that you left off has got to be dependent upon how much stuff you use, right? Like if I take a gram of this, and mix it together, there's going to be a different amount of heat than if I do a ton of this and a ton of this. You follow? The amount of stuff's going to matter. So the way that these things are written, these delta H's, these are actually kilojoules per mole, but we can't say that. And the reason we can't say that is because this is kilojoules per 1 mole of this. This is that many kilojoules per 6 moles of this, and it's that many kilojoules per 4 moles of this. So it depends on what you're talking about. So what this means, that there's negative 1225.6 kilojoules per 1 mole of P4. And there's negative 1225.6 kilojoules, negative 1225.6 kilojoules per 6 moles of Cl2, and there's negative 1225.6 kilojoules per 4 moles of PCl3. So it just depends on what you're talking about. You need to pay attention to the equation and the coefficients. So let's do an example. What is the change in enthalpy? So when I say enthalpy, what do you think? Flow of heat. What is the change in enthalpy associated with the production of 100 grams, let's see, of PCl3? Okay, so first of all, we're in grams. We need to get into what? Take a wild guess. Moles. Moles. Okay, so I'm gonna do my little PCl. I got 1. I got 3. Skipping, huh?
No.
What?
Wait. Kidding. Joke.
It's not funny, Garrett.
What did I miss? Just nose?
I don't know, you don't.
What?
Calm down.
We're not gonna tell you.
Calm down.
We're not gonna tell you. Possibilities.
Okay, so phosphorus weighs 31, chlorine weighs 35, rounded. That's 31. That's 105. So that's 136 grams per mole. So I can start out with my 100 grams of PCl3.
What's that mean?
PCl3. And I'm going to turn that into moles by getting rid of grams and going to moles. 1 mole weighs 136 grams. And then I can turn that into heat. Negative 1225.6 kilojoules per, well, how many moles in this case? 4. Moles PCl3. And this comes out to be negative 901 kilojoules. And this is also exothermic.
No, use the bathroom.
Yep.
How do we know it's negative 12.25%? Just from the example above?
Yep.
So it's the same question?
It's the same problem.
So you're
Yep.
giving it to us?
Yeah, I have to give you that delta H. Yep.
Okay.
Yep. Now, for now, I'll say for now I have to give it to you. Later on, you'll figure out how you can calculate that. Now, for whatever reason, I'm just going to tell you right now, whatever reason, it seems like so many people miss this when we get to test time. And I don't get it because it's a very simple thing, isn't it? You know, mass to mole conversions, you just got to remember, the real trick is that when you see this delta H written this way, that delta H is per however many moles are up in your equation. That per 1, that per 6, that per 4.
On the test, will the equation always be balanced?
Yeah, probably, yeah. I'm not going to pull tricks like that, probably. Okay?
So if it were to say the example of like P4, we would just do the same thing with the 1.
Yep, and that would be 1 mole. Yep. Good? Okay, so let's look at some homework. So that's it I got today. All right. So,